Okay, so this is section 7.1. We're still continuing integration by parts. This is part 4 to the integration by parts lectures that I've been doing. We've done a bunch of examples of different cases where we can use integration by parts, and we've seen how to apply some tricks to solve these integrals. Let's talk about definite integrals though. Take a step back. So let's say I have the integral from a to b u dv. So this is our integration by parts formula. The way I do this as a definite integral is I'm going to do, so the integration by parts formula is u v minus the integral v du. And then this goes from a to b now, and I just evaluate this at a and b and subtract them. And it's as simple as that. I just evaluate it now. This integral here has bounds. So we can do a quick example, not so quick, but we'll do an example where I do integration by, where I do a definite integral. So we're going to do the integral from 0 to 1. So we have the arctangent of x dx. And so again, you go through your mental Rolodex of what are all the different strategies we have: u substitution, direct integration. None of those work. So let's try and do integration by parts. So we need to pick a u and a dv. So there's really nothing, there's really only one thing we can differentiate here. That's the arctan. And then dv will just be everything that's left over, so it's just dx. So if I take this derivative of arctan is 1 over 1 plus x squared. Stick a dx there. V then is going to be x. So this integral then is going to be uv. So I'm going to get x arctan of x. Sorry, let me stick with the notation I started with. It's easier for me to write arctan. So arctan of x. I'm going to evaluate this between 0 and 1. I'm going to do minus the integral of v du here. And the integral of v du is, so I'm going to go from 0 to 1 again, and I'm going to have 1 over 1 plus x squared times x. I'm going to get x over 1 plus x squared dx. So this I can evaluate. We'll talk about that in a second. Well, yeah, let's go ahead and do it. So this is equal to, so when you plug in 0, you're going to get 0 for this first term here. So I'm going to get 1 times tan inverse of 1 minus the integral from 0 to 1, x over 1 plus x squared dx. And arctan of 1 is pi over 4. So 1 times pi over 4 is pi over 4 minus the integral from 0 to 1, x over 1 plus x squared dx. And now we need to do this second integral. So if you look at this integral, and again, you have to go back through your head and ask yourself, okay, can I do u substitution, direct integration? Do I need to do integration by parts again? Integration by parts looks like it's going to be really ugly. You'll notice that we might be able to get away with a u substitution though. I have a 1 plus x squared down here. If I differentiate that, I get 2x. And I have an x up here, so that seems like an integral I can do with u substitution. So I have pi over 4 minus the integral x over 1 plus x squared dx. Let's try a u substitution. U is 1 plus x squared. Du is 2x dx. So dx is 1 over 2x du. Sorry, I'm integrating from 0 to 1. So if I'm integrating x over 1 plus x squared between 0 and 1, I'm going to change these integration bounds. So you'll remember that I treat u as a function of x. I just plug in my original bounds. U of 0 is 1. U of 1 is 1 plus 1 squared, so 2. So this is the integral. So this is pi over 4 minus the integral from 1 to 2. So I have x. 1 plus x squared is now my u. dx is 1 over 2x dx. You'll see that my x's cancel. This is pi over 4 minus 1/2 the integral from 1 to 2, 1 over u du. And this integral we can do now. So this is pi over 4 minus 1/2 integral of u, 1 over u, ln of the absolute value of u, evaluated from 1 to 2. This is pi over 4 minus 1/2. So pull the 1/2 out actually. So minus 1/2, and then ln of 2 minus ln of 1. This is pi over 4 minus 1/2 ln of 2. And there are ways you can simplify this. I'm going to leave it like that, just because it's easier. So I think I'm going to stop there. There's one last example in this section. Yeah, so I don't think I'm going to do that. You're welcome to read it, though. It might be useful. It's pretty straightforward. But that's where I'm going to stop.